Well, I'll introduce you. We're very happy to have Seyda Ipek with us today, starting off our seminar season all the way from Irvine, and she's going to tell us about high-scale Qcd confinement and baryogenesis.
Yes. So I will start talking about the baryon and asymmetry of the universe, because this will be mostly trying to solve the problem of why there is more matter than antimatter. And we know that there is more matter than antimatter, and this is defined as the number of baryons minus number of antibaryons over the number of photons or entropy, and this is about 10 to the minus 10. And the other thing we know about the baryon asymmetry is from Sakharov. He said that any theory that wants to explain this asymmetry, the origin of this asymmetry, needs to abide by three rules. These are called Sakharov conditions. And one of them, the first of them is obviously your model needs to be baryon number violating. So there needs to be a baryon number violation. This could be lepton number as well, but I won't talk about lepton number violation today. So there needs to be some type of number violation, because we think that the initial conditions after inflation was matter-antimatter symmetric, because inflation tends to wash away everything you have, so they would have washed away some pre-inflation asymmetry. So if you start from symmetric conditions, meaning that eta equals 0, and if the baryon number is conserved, that number is always going to stay 0. So you need to have some baryon number violation so that there is some non-conservation. The second condition is that there needs to be C and CP violation. CP is kind of a handle to differentiate between matter and antimatter, so that tells you if your model is CP violating, that means the matter and the antimatter particles are behaving just a bit differently, such that it could produce an asymmetry. And the third condition is that all these baryon number violating and CP violating interactions needs to happen out of thermal equilibrium. And this is because in thermal equilibrium, any process that happens one way would also happen the other way at the same rate. So if you are producing some baryon symmetry, you would be also washing it at the same time, at the same rate, if you are in thermal equilibrium. So you need to go out of equilibrium such that one of those interactions is not allowed. Now these are the three rules that any model that addresses this problem needs to think about. And we can ask, we have the standard model, which is a great model. Can it explain the baryon asymmetry, and does it satisfy all these conditions? Let's look at the first one first, the baryon number violation. So in the standard model, we know that the weak interactions only cover left-handed particles. So the only left-handed particles are charged under SU2. And because of that, there is an anomalous particle number current, and the same is true for lepton number as well. But again, I will only talk about baryon number. So this anomalous current is given by the here W is the SU2 field strength, and W tilde is and this is also sometimes called, excuse me, a Chern-Simons current in math. And this corresponds to a number, which is, this current can give you a number, which is called the Chern-Simons number. Okay. And so in the weak interactions, weak interactions, this then produces some processes called sphaleron, which violate baryon number. So these are basically, you can think of this as your universe sitting in a potential with different baryon number or with different Chern-Simons numbers. So you have different ND here, this baryon number, and then this is some energy level. So at zero temperature, our universe sits at one of these minimums with some baryon number, whatever baryon number it has, and the solutions that will take you from one baryon number minima to another can only happen through instantons. So these are instanton solutions. And their rate is extremely stressed. It goes like e to the minus 4 pi over alpha weak. This is about e to the minus 167. So these are very small. So at zero temperature, let's say, at zero temperature, you wouldn't change the baryon. You wouldn't change your baryon number. You wouldn't expect, for example, any baryon number violating stuff happening at the LHC either. But if the temperature is a lot higher, especially if it is higher than the electroweak scale, you can have processes. These are just, instead of tunneling, you can just roll over this potential basically. And these are called sphaerons. And sphaeron comes from Greek for rolling over, or falling, I think. And the rate for these processes is a lot higher. It goes like alpha v t to the 4. It's actually, I think, 25 times alpha v to the 5 times 4. But when alpha v happens to be 1 over 30, so numerically it is just alpha v to the 4. So this says that at higher temperatures, these are temperatures higher than the electroweak scale, the baryon number violating processes are actually very efficient in the standard model. So let's put another column here, standard model. So the baryon number violation is actually a very easy and efficient process, about 100 GeV in the standard model, which is great. Because that's what you need for to explain the baryon asymmetry. Okay. I will just continue a bit more on this baryon number here. This is of course thermodynamically. This corresponds to a change in particle number. Corresponds to a rate over temperature and a chemical potential. This gamma is whatever. This is the rate of processes that change the particle number basically, and T is some temperature, and mu is the chemical potential. This will become useful later, so I want to just give their definitions. From that, you can calculate the baryon number, and gamma, for example, for sphaeron processes, gamma is T to the 4. And the baryon number then with these sphaeron processes would be given as from some initial time to a final time, gamma over T times mu, which also usually depends on temperature. And the definitions of temperature here are usually complicated because, of course, temperature is defined for a system that is in thermal equilibrium, whereas we say you need to be out of equilibrium. So one always needs to be careful about what temperatures, where do you define or when do you define your temperature. But let's not worry about that for now. Okay. So this is the first one. The standard model is really good at violating baryon number. How about CP violation? Because we also know that there is CP violation in the standard model. This is again in the weak sector actually. The CKM matrix has a phase. This is the quark mixing matrix. Has a phase that brings CP relation. And we observe the CP relation in neutral meson oscillations, which is great because we do need CP relation. However, I won't give you any details or technical details, but in order for this CKM phase to be involved in any baryogenesis process, one needs to have basically all the quarks to be involved, and the CP phase, or even if it is order 1 in standard model processes, it is when you involve all of the quarks, some of them come with very small Yukawa couplings, and the effect is just diluted by all the small Yukawa couplings, all the light quarks in the standard model. So it turns out that any baryon asymmetry will be about, like, the most you can get is 10 to the minus 20, which is like 10 orders of magnitude smaller than what you need. So this is a CP relation. Even though it exists in the standard model, it will never be enough for explaining for producing enough baryon asymmetry, because it is too small. Its effects are too small during baryogenesis. So this is one of the problems with the standard model baryogenesis, or the baryon asymmetry, and why we say baryon asymmetry, the existence of baryon asymmetry requires new physics. I will also mention that there is also no out of equilibrium process in the standard model. So even the weak processes are very much in equilibrium till extremely late times. The only place that the standard model could have had out of equilibrium conditions is during electroweak phase transition, and if the Higgs boson was lighter than about 90 GeV, standard model could have had a first order electroweak phase transition, which then would have satisfied the out of equilibrium condition. But the Higgs is too heavy, and the electroweak phase transition is just a crossover phase transition. Well, it's not even a phase transition, it's just a crossover transition. So these two reasons are why you need new physics to explain the baryon asymmetry. But it's also important that the new physics has to couple to the standard model, because at the end you are producing standard model particles. So, unlike, for example, dark matter, even though I really wanted to couple to the standard model, it could just happen to be just gravitationally interacting. But with the baryon asymmetry, any model that explains it has to couple the standard model, basically, which is nice, which is kind of nice. But today, I will actually start with not the out of equilibrium condition, but the problem of CP violation. So let's go back to saying that the only CP violation in the standard model is from the CKM phase. This is the only one we measured. There could also be CP violation in the strong sector. We are trying to measure the neutron EDM, which would tell us how much CP violation can exist in the Qcd sector, but it still can exist. And so, what about that CP violation? What about the CP violation in Qcd? Or maybe theta bar. So Kuzmin, Shaposhnikov, and Kachev, they asked this question also in 1992. So they said, so for this, you always assume there's an axion. And when there's an axion, you have this term in your Lagrangian, this theta bar and GG dual. And theta bar is A over F. Yes. And it is equal to the so this here A is the axion field, and from this and integrating out a pseudoscalar called eta prime, you can actually get to an effective Lagrangian, which will be relevant for baryon asymmetry. Like this. So this is just standard model plus an axiom. And this is the mass of the eta, and F pi is the pion decay constant. So when axion gets settles down to its mass, you have a GG dual condensate, which is given by d squared sine theta bar. And then you can plug this in here, which then makes your effective Lagrangian this. And usually the axion mass is temperature dependent as well as the angle theta bar here. So this is basically, and you can treat this as some field that depends on temperature that is coupled to the WW tilde term, and the WW tilde term gives you the anomalous current, anomalous baryon current. So this can be interpreted as, this is also called, it's very similar to spontaneous baryogenesis. This temperature dependent or time dependent terms here can be interpreted as a chemical potential.
Sure, I'm following. So the sine theta bar, the idea is that at finite temperature, the axion is not at its zero temperature minimum. So it's there's a non-zero bed for the axion that sort of is the source of.
Yeah, I will give what that MA squared is.
Yeah. Okay.
It is not so much,
Right.
The thing that will be important is that during a phase transition, axion mass and theta bar will be changing. So that change will be the most important part for baryogenesis evaluation. And you can kind of see here that. But if there is no change, there is no chemical potential, basically. So this is just, technical. I erased it, but that general baryon asymmetry can be given by an integral over T gamma over T mu. So this chemical potential here becomes that's coming from the axion. So for this case, it will be, let's call this part some factor C. By the way, I think I forgot to say, but right now I'm only reviewing the Kuzmin paper. And at the end, if I can give any spoilers, at the end they show that the Qcd axion actually doesn't work. But I'm just going through it as an exercise, because it will be important for what I will talk about later when I come to my work. So this is the number of baryons given by the change in the axial mass and theta bar. Also, some baryon number changing rate. So what is this gamma here? What is changing the baryon number? So as I said, for temperatures that are above the electroweak phase transition, these are spherderons, and gamma is equal to about alpha weak times temperature to the fourth. But these are for processes.
So can I just ask a basic question? So, I mean, if you're integrating out the eta prime is pretty low mass, right?
It's about
GeV.
yes, about a GeV.
So you can't really, it seems like you can't really use that effective Lagrangian. The temperature is near the electroweak.
Right, exactly. So let me just tell you.
Okay.
Let me just tell you. Well, this is, obviously it wouldn't work for just like pure standard model or standard model as we know it. So if you look at the thermal, this This is temperature, this is some rates. So this is gamma sphalerons. Above the electroweak phase transition, sphalerons are very active, but after the electroweak transition, they die off exponentially. And whereas, let's say this is the Kyle phase transition, or the Qcd scale. The other thing that we will be interested in is the axion mass. So axion mass just settles to its normal value, which is, I will give you later.
The temperature is going down.
Yeah, temperature is going down. So for infinity, this is 0. It's a bit easier for me to draw it like that. And this is one other thing that is important here is theta bar. And then don't worry about the scales. Just theta bar. So the mass of the axion and theta bar usually changes around the Kyle phase transition. However, as Marcus was saying as well, also I was going to say is, if I just look at the Qcd scale, obviously the sphalerons are turned off. So there are no baryon number violating interactions happening at the Qcd scale. They're exponentially expressed. So what people try to do is try to push the electroweak phase transition towards lower temperatures. So can I delay the electroweak phase transition until the Qcd phase transition, Kyle phase transition, such that the sphalerons are still active at the Qcd phase transition. So Kuzmin et al. They actually showed that if you start with a conformally symmetric Higgs potential, so without any mass terms, you will of course get a one loop effective potential, like a one loop Coleman-Weinberg, to break the electroweak symmetry. However, even when you are doing that, so you start with a symmetric Higgs potential at high temperatures, and then at some scale, you kind of electroweak. Even though you have a larger minima, this barrier is still too high with this. If you start with a conformally symmetric Higgs potential, the barrier is still too high that you wouldn't be able to tunnel or go above the barrier until the Qcd phase transition. So this is at the electroweak scale and even smaller. Let me draw that one a bit higher. When you get to the Qcd phase transition, your Higgs will get a tap volter because this is not full, obviously. So this tap volter will just tilt the Higgs potential, and this way this barrier becomes a bit smaller, so you will go through the electroweak phase transition. But until then, the Higgs just stays at the zero valve, hence the sphalerons are active till very small temperatures.
So in some way, this is like saying that you can have some extremely first-order phase transition.
Yeah, this is super cool. But actually here, the more important phase transition is the Qcd phase transition, which I was just about to mention. In this case, since the Higgs is in the symmetric phase at the time that the Qcd phase transition is happening, all the quarks are massless, and if you have more than 3 massless or very light quarks, the Qcd phase transition happens as a first-order phase transition. This is from lattice results and also some
Even the
theoretical
electroweak, that
arguments.
was really allowed, and even in 1992, this kind of story.
This
You
was,
need to have a very
oh,
light
yes.
pig.
So
right?
let me, yes,
You have a
that
very
is
light
that's
pig.
the other reason. That's actually the reason why they decided it wasn't allowed. Because it's not just this, but let me just go back to what the baryon asymmetry is. So can you wait like 2 minutes?
You're in charge.
Good. So the general idea is this, that the electroweak phase transition would be triggered by the Qcd phase transition. So what will be happening is that Qcd phase transition will happen as a first order phase transition because you have massless quarks. So, and a first order phase transition proceeds via what is called bubble nucleation. So you have basically your universe is mostly the Qcd hasn't confined. But then there are some thermal fluctuations where the Qcd will be confined, and then this confinement will trigger a Higgs phase transition. And how the Higgs phase transition happens doesn't matter as much. It could happen via some via first or second order phase transition, but there will be bubbles. And outside the bubble, the axion mass or theta bar is very small. And inside the bubble, it will have some finite zero temperature value. And what this change is important. So this, how the axion changes through the bubble is very important. And it can be given. The finite temperature mass can be given from parametrically. This is the zero temperature mass times lambda over T. People calculate this and find different results, but the idea that it is very small is decided, I think. But this is from I don't remember the calculation now. I think from 80s. I think Mark and Kolb and Turner did this. And of course, the zero temperature value is from a dilute instanton gas approximation is what it's called. This result, and it's not exactly 7; it's like 6.8 or something like that. That exponent. But then the change from lambda t to the 7 to this value then help you with the baryon asymmetry production. And let's assume that theta bar is changing through the bubble as well, but let's assume that it's just not changing and it's order 1 or some value that we will need. The number of baryons will be given by all the way to the 4 is from Speyderan processes, and this is again coming from the Speyderans. This is the temperature of the phase transition, temperature when the Speyderans are turning off, and this is coming from this is again temperature of the phase transition. This is from the change in the axion mass, and sin theta bar is just the theta bar angle. Now, we are not just interested eta b and b, but eta is given by nb over usually the entropy density, and this will be given by entropy. This is important. This is the entropy is this is right after the phase transition. And I will call this temperature T reheat, whatever the temperature after the phase transition.
Sorry, so can I just
Yes.
see if I'm following? I thought the picture is the picture that Qcd phase transition triggers the electroweak phase transition.
Yeah.
That's the picture.
Yes.
So then the bubbles of true vacuum have. I'm just wondering because it looks like you've drawn a bubble there that has or QCD condensate, but H equals 0? Should that,
No, that's V. Sorry.
That's a V. Okay, good. Okay, I just
Yes.
want to make sure I'm following. Okay.
Yes,
Thank you.
sorry.
Mhm.
So this is, again, this TV heat is coming from the entropy. And lambda is the QCD scale. This numerically, this is about 10 to the minus 9, which is very close to what we need. Over the phase transition temperature, over the reheat temperature, meaning the temperature right after the phase transition, over lambda QPT to the 7. Now, if you, so in this model, lambda will be basically equal to TPT, the phase transition, because we delayed the phase transition to whatever the QCD scale is. Lambda QCD. However, after the phase transition, when the Higgs goes to its true vacuum, there will be some more entropy generation. This will be equal to whatever the potential difference between the vacuum at Higgs equals 0 and the true vacuum. And this is usually proportional to the n Higgs, the Higgs mass to the 4, the energy. Then the temperature after reheat will be about the Higgs mass. So with the Higgs mass of 100 GeV and a lambda QCD in the standard model is about 100 MeV or 1 GeV, this will give you a huge dilution. Unless Higgs is extremely wide. So this is about 2 eV over 100 GeV to the cube. So they decided that this will never happen because even then Higgs of, I think they needed like a few keV Higgs or MeV. So even then it was not really viable. But this is the main reason actually they decided why you will never ever be able to use the theta bar to produce a baryon asymmetry because.
So if the Higgs is that light, why is there such a big solution?
This is with not our Higgs.
Okay.
Now we know the dilution, but they said.
But then also, it seems like I don't think this whole thing could possibly. I mean, I don't think you could get into this sort of scenario where the QCD is inducing the electroweak phase transition, unless you had a very, very light Higgs, I would think, or?
Why not?
I mean, basically just the energetics, right? I mean, the point is that the QCD phase transition, the scale is sort of a GeV,
right.
and that is adding to the, so that means that the electroweak potential has to, be flat on that scale, right, for QCD to even have an effect.
So I don't remember what Higgs mass is. I'd written also worked this out, I think, so I don't remember how much you need to tilt this potential. I don't remember how big the barrier is. I think that's the more important. This is not your
model anyway, so maybe.
Yeah, it's not my model, but even with that, I think the more important thing is how big this barrier is, more than how big, more than comparing the Higgs versus other scales. You need to compare, just like how large this barrier is.
Well, but you want the tilt to push you over that barrier, or you said
it is still tunneling.
It's still first order. It's still
it's still tunneling, but it's just easier to tunnel.
Yeah, but it's okay. All right, go ahead.
Okay.
I'll ask
Well,
my questions when we get to the real model. I want to see the real model.
I should actually check that. That's true.
Okay.
Okay, so this was again. This was just showing you why it wasn't working, and I still wanted to make something like this work, and I actually really got excited after the Nucleation models came out, because that intrinsically couples a QCD phase transition to a Higgs phase transition. So I really wanted to have that connection work for baryogenesis. But Nucleation models, of course, they are problematic for many reasons, but they're also very problematic for baryogenesis reasons. So I won't go into that part. Well, we can talk later if you want. This was a bit, so this one, what I'm going to talk about is a bit different than that. It is instead of, so what Kuzmin was trying to do, and also Geraldine Sarvant and others did work with some other model that also pushed the electroweak scale to the chiral scale, and we can talk about this later if you want as well, but I want to mention them as well. So Kuzmin and Geraldine were basically the only people, they were only people who looked at the Qcd transition in terms of employing it in baryogenesis. So they were doing is just pushing the electroweak transition towards lower temperatures. Tim and I decided if you can do it the other way around, if you can just raise the Qcd phase transition temperature so that the confinement is happening above or around the electroweak phase transition. But this is not this does not answer any fine-tuning problems. There's no reason why it's not. The Qcd phase transition will not give us the electroweak scale. It is just they will be happening around the same time. So to raise the Qcd confinement, so we know that Qcd confines because the Qcd coupling constant, or alpha S, kind of blows up around 100 MeV. So it becomes very large, or becomes larger than about 4 pi. So that the Qcd confines. So we were asking if you can work with some effective Lagrangian. So just consider this without worrying about where it comes from. This is not GG, this is just GG. And it's phi is some scalar and m is some scale of this effective operator. And GS0 is the Qcd coupling constant. But together this term defines a new coupling constant, which depends on some field phi. And it just changes the standard model coupling constant by a bit. And let's also assume a potential for this phi. It doesn't have SD2 symmetry. For values of these alpha I at about TeV to the 4 minus TeV scale, or whatever dimensions they need, with this potential phi gets a web. It is also about a few TeV. So when phi gets the web, your strong coupling constant shifts a bit. And you can tune this phi web to cancel with whatever the value of your strong coupling constant at some temperature. So what we wanted to do was, we don't have colored chalk. What then we want to do with this is basically make this just go like this. At some temperature we pick, and let's pick it as to be TeV.
So this is a copy of QCD?
This is exactly QCD. We're just adding this term, this effective coupling. And this can come from, for example, a triangle diagram with some heavy quarks running inside. Let's give one example to see this.
But you're going to explain in a while why the proton doesn't weigh a TeV.
Yes. Good. Very good point. But let's not worry about...
Phi level is well, for right now, phi is level 0 or phi
so that depends how you want to get rid of phi. So that
your origin.
Right. So that is...
Okay.
Let's talk about UV completions just a bit later. Is that okay?
I'm just wondering, in your normalizing or whatever, what is the phi level right now? I mean, you can always do a shift, right? Define,
Right.
okay.
So there are two routes you can take. One of them is phi is just some heavy particle that it has an FUT
I'm just
right now.
your convention.
Yeah. So that's our convention. So we have two ways to talk about phi. One of them is it is some scalar still with a FUTV web. And then there's another scalar which will help us to get rid of this effect later, with a FUTV web. The other one is phi goes through a symmetry restoration phase, and then it can be waveless right now. But then there will again be another scalar who can occur as a wave
So, sorry,
as well.
well, are you still asking you a question, or can I?
Yes.
Maybe a related question, or maybe it's the same question. So the picture is that phi is undergoing a phase transition at a TeV, and so its change of its value is changing the QCD coupling, and so it's just making QCD confined at a TeV.
Yeah.
Right?
Yes.
Okay, so delta phi at a TeV is of order of TeV or something. I think, and she hasn't told us where the origin is, but somehow, I think so far
Well, at
that's
the end,
important
you will
thing.
have to go back.
Yeah, that's my
Right.
question about why the proton doesn't weigh at
Right,
TeV,
right.
right? She hasn't gotten to that yet.
Yeah.
So. Okay,
Okay.
yes?
Good. So with this, let's say that we made QCD confined at a TeV scale. And again, similar to what I talked about before, so at this TeV scale, again, quarks are massless, but when QCD confines, you will have a first order phase transition with QQ bar condensates, and then these will still be of order the QCD scale, which is now TeV. And this confinement similarly will trigger a Higgs phase transition, which will also be of order. It just tends to be a bit smaller than the lambda, just a lambda over 4, I think, if I remember.
Are you
Yes,
gonna-
lambda over 4.
Are you gonna find, I would expect that you would find that this scale M,
Mm-hmm.
so this coupling phi over M, if M is smaller than a TeV, significantly enough smaller, then that represents a strong coupling. This phi GG term
Right. So
is
this,
strong at a TeV.
sorry,
And I
this,
suspect that you may need to be in that regime in order to have the trigger, or you're saying that's what it would need to be?
yeah, that's where you need to be.
Okay, thank you.
This is not strongly coupled. But that is one option. You can have some QCD prime that is strongly coupled, then couples to the standard model.
No, but that answers my question.
Yeah.
That's sort of
Yeah.
a relatively weakly coupled value. that
Yeah,
could-
yeah, it is. So again, this is the similar picture where a QCD confinement triggers a Higgs phase transition, which then this time you can get exactly the same baryon asymmetry, which was TPT over TBG to the cube. To the 7 times sin theta. But now, since the Higgs web and the QCD, the condensate scale or the confinement scale is similar, you don't get, this is all about the TeV, and also lambda is about the TeV. You don't get any suppression, so this will be the nicety of it, obviously. However, as it came up, this also means that if the QCD confinement scale is at TeV, you have pions that are very different than your normal QCD. Let's not talk about pions, but F5, which is also some number times F5 and then this chi is about exponential of for 0.6, this is about 1,000. So all stuff everything that depends on the QCD scale will be heavier. Like protons will have about a TeV mass. There will still be a proton-neutron split. There will also be more pions than normal because you have like all the quarks are massless, and then after the chiral phase transition, you have the QCD condensate, but that will give you just more pions compared to having only two of them massless. There is also the symmetry rating is different. The phase transition will be a bit different as well, but the main thing is that your QCD particles will be a lot heavier. So obviously you need to go back to the normal QCD before BBN. Although we haven't checked yet, we don't know how much before BBN you need to go back. So the only thing we know about the early universe, the earliest thing we know about the early universe is BBN. So this is T. This is BBN, and let's say this is the scale lambda QCD. So BBN is about MeV. Normally, the standard model QCD is 100 MeV, or let's say proton mass about GeV. So lambda QCD, right now we are changing it to TeV. But obviously it needs to go back to the standard model value at some point. It's very bad. You know what I'm saying. It needs to change from the standard model value it needs to change from a TeV to a standard model value before the time of the BBN. Because at the BBN, protons were, or maybe a few MeV, the proton and neutron mass is about a GeV, and they continue to form the light nuclei that we observe now. And we know that the light nuclei, as our nuclei, consists of GeV protons. So this then tells you that the QCD scale, which depends on the phi value, is it's dynamical. It depends on a value. It needs to go to lambda QCD standard model. So it needs to change from TeV to GeV, which is not an insanely different, insanely high change, but still needs to happen between TeV and maybe 100 MeV. And to do that, we are currently looking at a couple of different ways. One of them is that the scalar field phi can couple to another scalar field, which can go through a phase transition while this phi is going through a symmetry restoration phase. So
sorry, just maybe just to go back a bit, just to make sure I'm following. So before we get to this part, even without this, the idea is that the electroweak phase transition is now raised to a TeV?
Yeah, it's still
QCD
triggered by
is
QCD.
now basically
inducing
this.
It is still triggered by QCD.
So it's actually larger, happening at a higher temperature.
That's true. So depending on how this change happens, if you, for example, say phi valve became 0 at 100 GeV or a bit less, that will be below the electroweak scale. This will just change the Higgs wave from a TeV to 250 GeV as value. So you can just.
So this vacuum for electroweak that's being induced from this QCD, this high scale QCD transition, that vacuum has nothing to do with our vacuum. I mean, it's very different.
Yes.
Like the Higgs band, Higgs mass are very different.
Yeah.
So in a sense, there's also a kind of second electroweak phase transition that's going to happen, in the sense that you go from that vacuum to our vacuum, right?
That's true, yes. Yeah.
Are you going to talk about that, or?
No, I won't, because we are not, we haven't did any details on that yet. But I can just tell you my hunches for what's going to happen.
Well, why don't you go on, and we can come back to that at the end of your talk.
Okay, well, I kind of lost my count anyway. What was I
Oh,
saying?
okay, well,
yes.
you're in
So,
charge.
yeah, I was going to say. So, one way is to get rid of this is high web will be go to zero, so it's the symmetry restoration. And these kind of potentials, like the scalar field potentials that go through a symmetry breaking and then a later symmetry restoration phase, these exist. Michael Ranzimusov, he started working on these things a couple of years ago. So this just wouldn't require other scalar fields that couple to phi. But it's not, hopefully it is not like way too complicated. The other way to go back to normal QCD is have another field. So we had this term, and then basically add some, or we had this term, and then have some other field psi, a scalar again, with some other, say M1, M2, and then some cancellation between these two terms. So say psi is another scalar field that acquires a web, and then just fights against this phi term, and then they kind of cancel. They don't need to cancel perfectly, but they kind of cancel to get rid of the new QCD scale, let's say. This is a bit, maybe this is more fine-tuned than anything. But so currently we are working on this part, and especially as Marcus was saying, how this affects the electroweak phase transition is important also for baryogenesis, because, for example, you don't want to turn on sphalerons because then they would wash out by asymmetry, or you don't want to dump too much entropy to the system, then again you would wash out by asymmetry. So these parts are important also for the baryogenesis theory, the baryogenesis story that I was talking about. So, but depending on which route you take for UV completion and also the IR completion in a way, it will always have some important things to say for collider constraints, because these will require definitely some new colored particles or scalars that are that can already be searched for at the LHC, and everything will be about a few TeV scale.
I mean, there is another possibility that you could consider, which maybe it's a topic for discussion afterwards, but you could actually, instead of trying to make QCD do this, you could just have another QCD that does
That's
this.
true. Yep.
And it could actually be inducing electroweak symmetry breaking in our vacuum today, and you wouldn't have to do. Of course, you would pay the price of a new strongly coupled sector, but you would have, in a way, a simpler cosmology.
That is true. I think that has been done, actually. Because then you don't need any of this phi theory. You can just say there was a QCD that confined earlier, and that was coupling. I think Nathaniel Craig and John Marsh-Russell, maybe.
Oh, okay.
They did some. I can send you the paper.
Yeah, I'd be curious. Thanks.
But they weren't like worried about the normal QCD. They just said there's some hidden QCD which happens to confine a TeV because we don't know anything about it.
I'm just saying that the particular scenario I'm thinking of is that this is something that I've written papers on with Spencer Chang and other collaborators, that you can have a positive Higgs mass squared in the potential.
Mm-hmm.
Okay, so by itself there's no electroweak symmetry breaking in the Higgs potential, but then there's a tadpole induced from some strong sector that confines around a TeV.
Mm-hmm.
And so it's actually kind of a combination of Technicolor and the standard model, but it's actually still allowed. It doesn't have any of the phenomenological problems with Technicolor.
That would be great to look at how baryogenesis.
Yeah, so I was actually a long while ago, actually, I think when I first met you, I was talking at least with Anne, maybe not with you, about how baryogenesis would work in that scenario.
I would be really interested to look
So I'd be
at.
very interested to talk with you about it.
Yeah, let's talk about that later. But I should admit that I love to tell the baryogenesis part of the story, but Tim is more interested in more cosmological side of this story that has no other implications. So like, yes, baryogenesis is great, but then the question that if this is still allowed just by cosmological observations is an interesting question to ask. How can we tell that nothing weird happened to QCD before BBN basically? And one way to test it is say, oh, what if the QCD scale was different than a GUV in the early universe? Are there any observables that we can test against? Yes, the proton mass, but then, yes, let me give you a time-varying proton mass. Can you test this? So we are looking into that arena as well. Like, what would be different in a universe that had a dynamical QCD scale? So one thing you can look at is there will be some period of early matter domination, and you can say, oh, maybe that will give you a constraint on how high you can have the QCD scale. And that's one way, one possible constraint. The other one is to look at some dark matter models to see if they work differently in a QCD like this. Because now when you look at dark matter like freeze out, now you don't have massless quarks anymore at the KV scale. You actually need to confine to the heavy protons basically, annihilate into the heavier QCD particle, heavier confined particles. So that would be different for probably for WIMP case scenarios. And specifically for this one, the other one is looking at the axion, because for like other QCD, like other hadrons, axion mass would also be heavier, and then it will also be changing with time or with temperature. So that will be interesting to see if such axion is also still a dark matter candidate or not, or if it does anything funny to the QCD theta angle problem. So these are like several other ways that that are interesting just on their own. But for me, baryon asymmetry problem is dear to my heart, so I wanted to talk about that part today.
Have any more questions? I had a potentially stupid one, which is, could this possibly affect or maybe get any hints from things like the lithium problem?
I don't know, and I don't think I would ever know. For me, the lithium problem seems to be too complex to explain with one thing or another. But my first guess would be no, because lithium is produced quite late, like not even at BBN, but at about a few keV, I think. So you need to change something, around then, like for example, some energy or ionized electron fraction, something like that, to change the lithium density, I think. So my first guess would be no.
Okay.
But, yeah. The lithium problem is that we have more lithium than we have. We have less lithium, primordial lithium, than expected from standard cosmology.
Any other questions? If not, let's thank Seyda again.